and quantum model. And today we'll just talk about the quantum model in details. I have already introduced you all to the Schrodinger wave equation. What is Schrodinger wave equation? Loudly. What is it? H operator psi is equal to E psi. This is something that we've already discussed, right? If I have to talk about quantum model, quantum model of, this model is model for what? Model of an atom. I want a nod or an answer from all of you all, so that I know that each one is like paying attention here and not sleeping otherwise. So here what we have is, last time we talked about the quantum model and we stated that this quantum model had to be introduced because the last model had failed. What was the last model? Who gave the last model before the quantum model came up? Bohr? You know that I told you a story right in the very first class of atomic structure. Then how did it start? Dalton, this, and we've already revised it thrice, so I'm not going to do it again. But how did we actually, the last model that was given was by Bohr. The key special feature was that he was also one of those who was banking upon the Planck's hypothesis. What was Planck's hypothesis? It was the hypothesis which talked about the quantum concept. That means what was it? The energy levels are existing in orbits, and then he talked about discrete orbits for each level, and then he also stated that you have the angular momentum to be quantized. What was the expression for that? mvr is equal to nh upon 2 pi. But again it failed. I gave you many limitations also, because of which Bohr's model was actually not taken up for any further, or it was not enhanced, because you go on to enhance a particular model if it goes accepted widely, if there is no problem with the model. But there were problems with the model. Some of the problems were like the Zeeman and the Stark effect could not be explained. But the major things were like it did not talk about the dual nature of the electron. It did not talk about the de Broglie's principle, which was given later. When was the Bohr's model given? It was given in 1913. When did de Broglie give his principle? Almost 11 years later. So de Broglie gave his principle that your the electron will not only act as a particle, not just the wave motion, but it will not just have the particle nature, but it will also behave in a wave. It will also have the wave nature. So basically this dual nature was talked about. And what was the expression of de Broglie that was given in 1924? Lambda is equal to h upon p, which is where p is your linear momentum and is equal to m into v. Okay, that thing is clear to everyone. And the second thing because of which Bohr's model failed, these are like by and large, I give you many limitations, but by and large two main limitations were like it only talked about a single nature of the electron, and the second thing was like it did not consider the Heisenberg's uncertainty principle at all, which states that the position and the linear momentum cannot be simultaneously and exactly determined. But what was the Bohr's model talking about? It stated that you have discrete orbits. So if I give you a particular energy, you know that your electron will be at a particular position only. Getting the point? Whereas now I am telling you that according to the quantum model, the concept that came up was that you have a nucleus, alright, hypothetical. Hypothetical means this is like not something which is in actual or reality like this. Okay, so you have the nucleus and then you have the electron revolving around the nucleus, and this electron is not exactly revolving in a particular shell, but then it has a probability of going here, there, everywhere around that particular place, right? If I allow you to freely move around and then take this class, so maybe you will just maximum at the most lie within this classroom only. So there is a probability of the electron also to be moving in a particular space, in a particular region of the space. So here all you have the probability that the electron may be existing like this. This is what Heisenberg's uncertainty principle is all about. It states that the position and the linear momentum cannot be simultaneously and exactly determined, right? But Bohr stated that it will be in a particular orbit, but in reality it is in a spherical shell. You get that? But if I talk about the 1s, it goes something like fully spherical with no nodal planes. You remember that? Now let me just talk about these things in detail. The most difficulty actually arises from this quantum model only, because you get confused when it comes to Schrodinger wave equation. First of all, remember that quantum, anything that is quantum in nature, you talk about microscopic entities. This was clear to everyone even before. When you are talking about microscopic entities, it is also considering all the laws which are applicable to the microscopic entities. What are those laws? Now primarily two, the same footsteps. If you suddenly find out something which is miraculous, how will you bring it forward to the entire world? You will be publishing a paper in some international journal, because scientists read it and then they get to know about it. So both of them, Schrodinger and Heisenberg, independently gave their own models of an atom. Both were based on quantum structure of the Planck, and both were taking up the Heisenberg's uncertainty principle and the de Broglie's principle into account, and they developed a model. But the model that we study, and what happened, both of them published their papers simultaneously. Maybe one published in some month of 1926 and the other published in some other month. There was a very less gap between the two findings. But the energy that came out from the atomic structure of the hydrogen atom that was proposed was exactly the same. The results of both of them were exactly the same. Now when I talk about Schrodinger wave equation, this is primarily based on the wave nature. It's like talks about the wave motion and then it talks about the other things. Your Heisenberg's model was based on matrices. You are doing matrices and determinants also? You will be doing, or you have an idea about matrices and determinants? No? There is like something in maths that you will see as 1 0 0 0 1 0, something like that, or 2 3 4. You have some kind of matrices and determinants which are actually used by Heisenberg. So his quantum mechanics is known as matrix mechanics. Okay, the entire story was told to you to remember this. Quantum model was given by both the scientists, Schrodinger and Heisenberg. None of them cheated each other's work, they were independently working. Okay, but the problem with the Heisenberg's was his was a little complicated, because it had all mathematical numbers and then interaction of those terminologies. So the one that Heisenberg proposed, quantum mechanics that Heisenberg proposed, is known as matrix mechanics, and the one that was given by Schrodinger is based on totally your Schrodinger wave equation. Okay. Now I hope you all remember that this wave function is defining your electron completely. And if I have two electrons, then I will have two wave functions. One for the first electron and another wave function for the second electron. That means each microscopic entity has its own wave function. This is also something you know. Now let me just throw light on this equation again. I told you that this is some kind of an operator. That operator is generally in the form of some differential equations, some differential form only. So say supposedly if it is, this is just an example to make you explain again. If this was d by dx and then I had a function like e to the power minus 2x. Okay. So now this is the value of my wave function and this is my operator. Any operator, say I say A operator. Generally we talk about the energy operator, but here I am just arbitrarily taking any value of the operator. Okay. So I have, this will be the operator because I will operate this on my function. If I am getting back my function, what will be my function? E to the power minus 2x along with a value. What will be that value? Minus 2x. All of you all know that much of differentiation. Then that means I am getting my function back. I am getting my function back along with a value. With this value belongs to my operator. Understood? I repeat. All of you all pay attention here. Stop writing. I am talking about Schrodinger wave equation. What is my Schrodinger wave equation? Simply H operator psi is equal to E psi. This I made you Just learn it up like that. And let me tell you, remember that this equation was a postulate. Did I make you understand the meaning of a postulate? Postulate is something which is given just like that, and then it is like confirmed. So then here you have an operator. Look up. You have an operator. That operator will operate on a function. If that function is something that is coming back along with some value, then this value belongs to the operator. What does it mean? It means that मान लो that this may be the position, say the linear momentum operator. Let this be linear momentum operator. ठीक है? Now linear momentum in macroscopic entities or generally is mass into velocity, and even for microscopic it is mass into velocity. But उस operator को use करके I apply it on my wave function, I get my wave function back, then this minus 2 belongs to the linear momentum value. Got it? So the main benefit of having the wave function is that if you have the wave function, you can put your respective operator on it, and when you get back the wave function along with that value, then that means you are getting the value of that property. So that means if you know the wave function, then you can get to know about other properties also. Yes. The doubt is that what is the meaning of physical meaning of the wave function. Now wave function means that say supposedly I am saying that this is my electron 1 and I have time and again repeated it. What is this what does this electron, how will I define this electron? Because this is also E, this is also E, this is also E. I'll have to give them names like Chunnu, Munnu, Tunu, whatever. So then in that case I will actually assign them a wave function. Now the point is, this is a microscopic entity. You are saying that there are 3 electrons, but I am not sure because I cannot just see them easily, right? They are not visible as it is from the naked eyes, not even an atom. But then these are like 3 wave functions. Now so that is why these can be either real or imaginary. This is also, they can be either real or they can be imaginary. If I talk about it to be imaginary, then in that case there is no significance. And right in the, I think first or the second class I did talk about it, that you consider yourself to be the topper of this class, right? Maybe you were daydreaming or that's a dream of yours, but till you dream about it, it has no physical significance till you prove it in reality. So you have to attach a physical significance only to the wave function only when you have say only a real entity. And how do you make it real? Say if my wave function is, I gave you a very simple example of, this is the example that I generally take. If your wave function is a plus iota b, because I don't know whether the wave function is there or not there. If it is real, it may be just simply a plus b. So, and if it is imaginary, it may be a plus iota b, but I do not know whether it has any significance or not. So there is no physical significance. So your question was, what is the physical significance of wave function? There is no physical significance. But literally if you ask the meaning, it defines your electron completely. And this energy value, I'll just come back to it. Now I took an example of I took an example of some A operator psi is equal to E psi. I took this example into some value, say A psi. Okay, I stated that whatever value you are getting back will belong to your operator. So this in this case is your Hamiltonian operator. Your Hamiltonian operator is the energy operator. Energy operator means that this contains in itself the kinetic energy plus potential energy, which can also be written as kinetic energy operator, the way you want to write it. This Hamiltonian operator is your energy operator. ठीक है? and because it is an energy operator, I said अगर linear momentum operator लगाओगे तो value जो मिलेगी वो किसकी होगी, linear momentum की. तो if I am putting energy operator here, whatever value comes back will be the energy value that corresponds to your, that belongs to your Hamiltonian operator. Clear about that? And these type of equations where you get back the wave function are known as eigenvalue equations. These are known as it is also a kind of an eigenvalue equation only, value equation. And some more points that you can remember about them is that Schrodinger wave equation can be solved exactly only for single electron systems. It is a postulate. Postulate means there is no derivation. There is no derivation for Schrodinger wave equation. And another thing is, you can write the Schrodinger wave equation for even multi-electron. Schrodinger wave equation को लिख सकते हो मल्टी इलेक्ट्रॉनिक सिस्टम्स के लिए, पर सॉल्व नहीं कर सकते. समझ में आया? क्योंकि एनर्जी ऑपरेटर आप लिख सकते हो पर सॉल्व नहीं कर सकते. Got it? Okay, then another thing about this Schrodinger wave equation is that what is the purpose of doing it? It is like giving you two solutions. One is that it tells you about the wave function which gets solved completely, and the another thing is like it also talks about the energy. It also talks about the energy. And as you know that this wave function has no significance, so therefore this is really known as the probability amplitude. In many books you will also find the representation for probability density as psi square. And the example, although we have taken it once, I am taking it up once again. If you take A plus iota B, if I multiply it with its complex conjugate, then what will it be? A minus iota B, that will be A plus B into A minus B is A square minus B square. So that will be A square minus B square. What is your iota square? Minus 1. So iota square becomes minus 1 and this total becomes plus. So this becomes real. This was clear to everyone already. So but then this probability density is psi into psi star, or in many of the books it's written as psi square also, which means that we are taking the wave function to be real, we are assuming it to be real and then multiplying it with its complex conjugate. So a real into real will always be real, and a real into its complex conjugate will also be real. Any physical significance for this? All of you all say? No. And physical significance for this? Yes, because it tells you about the probability of finding the electron in a given region of space. Okay. Then normalization and orthogonality, we've already done it twice. Just reminding you that normalization is psi into psi star into dx is equal d tau is equal to 1. Is your which principle? Normalization. And if they are the same level, if they are different levels, and this will be equal to, all of you all say that? 0. So that even if you are not paying attention, it goes in the head somehow. So it is 0. Now the point is that when we get this wave function, what do you do with it? आगे इसका क्या, psi square तो एक value होगी, उसका what do you do? Now the point is, you can actually plot this wave function versus say R. Okay, let me tell you the wave function. Now you know that what are the solution of the solutions that you get from this Schrodinger wave equation for hydrogen atom and similar systems. Similar systems matlab single electronic systems. So when you solve them, you get psi, E, and there is generation of 3 quantum numbers also. Now help me to recall what are those quantum numbers? N, L and M. Alright. And from here now you know that earlier you used to remember your K, L, M, N shells. Now these quantum numbers give rise to what all shells? S, P, D, F. and the main shells are like 1, 2, 3, 4. No relation with this. The main shells where n is like a quantum number are like 1, 2, 3 and so on, right? And then you get information about now the new shells. Those are the S, P, D and F. This much you remember. Now if I have to talk about this, the thing is like this psi will have some expression and it will be related to your R. R is the distance of the electron from the nucleus. ठीक है? तो distance of the electron from the nucleus means that when my R is 0, I am talking about this position. All of you all look up. Understanding is more important now, so that whenever whatever questions you get, you can tackle them if you have the understanding. What is this R? R is equal to 0 means I am here. R is equal to some value means I am moving now away from the nucleus. Okay, so this is the R, that is the distance from the nucleus. Now psi will be some expression in terms of R. I am not writing the expression because it looks complicated. No need to remember that. Now the moment I substitute, how do you plot? R की value 0, so you will check out what is psi. R की value 0.1, 0.2, 0.01, 0.2, whatever. You will keep substituting the values and you will keep getting a value of psi, right? You take up different values of R and you will get. So basically mathematically solve करने के बाद, it is important that you plot the graph also. And how will you plot? This is like, it comes something like this for 1s, because 1s will have its own expression. Thoda from the top, understood? So this is how it will look like. This diagram is given even in your NCERT books. So, but is there any physical significance of this graph? Say confidently, is there any physical significance of this graph? Why no? Because it is talking about wave function. Say it confidently now. Is there any physical significance of this graph? How can I attach physical significance to this graph? By taking the square of the wave function or the. So then in that case, that means I should be taking what? Psi square or versus R. I am writing psi square because in your books it is given as psi square only. But what is this psi square? Psi into psi star only. Now here when you have your psi here, if I even take the square of this, you know that it will look something like this only with increased values. Plot to same ही होगा, क्योंकि even if I take the square here, now can I attach any physical significance to this graph? Yes, sure? Yes, ma'am. Why? Because this will now be real, and that is real entity and it has a meaning, a significance. Now what does it mean? Let's look at the graph. Look at the graph. Now here what you have is, when your R is 0, there is maximum probability of finding the electron. यही मतलब है? When R is 0, there is maximum probability of finding the electron. इतना समझ आया सबको? But is that correct? जब मेरा ये 0 है, there is maximum probability of finding the electron here? Yes? 2, 3 saying yes, 2, 3 saying, समझ के बोलो. What I have here is, when my R is 0, I already showed it to you in the graph. Sorry, in the diagram. That if this is my nucleus, my 1s will be somewhere away from the nucleus like this. Alright. Now R is equal to 0 means in the middle of the nucleus, because it talks about the distance from the nucleus. So this diagram is giving you a picture. This is probability density plot. What is this probability density? So probability density plot. What is this giving you a picture? This is giving you a picture that there is maximum probability of finding the electron when R is approaching 0. So इसका मतलब तो है that the electron is there at the nucleus. But is the electron there at the nucleus? So is it giving you a correct picture? So that doesn't mean that Schrodinger is failing. The problem with this diagram is that it is not giving you any connection with the volume element, because electron, when it is, you have your nucleus here, the electron is revolving around the nucleus, right? Now if the electron is revolving around the nucleus, it is revolving in a spherical shell. ठीक है? तो R का मतलब तो है कि हमने distance ले लिया from the nucleus. लेकिन उस स्फेरिकल शेल का भी तो अपना कोई वॉल्यूम है. शेल का वॉल्यूम निकालना सीखा है ना आपने. हाउ डू यू फाइंड आउट द वॉल्यूम ऑफ अ स्फेरिकल शेल? मान लो, लुक हियर, this is your nucleus, or say let the nucleus be here, let the electron ka shell be here. So if this is r, this revolves in a distance of, let this be dr, ठीक है. तो इसका वॉल्यूम क्या होगा? वॉल्यूम ऑफ अ स्फीयर, आउटर स्फीयर माइनस inner sphere. The purpose of telling you is that this volume element should also be considered. You are talking about the probability density in some region. What is that region? This volume of the spherical shell. And this shell, when you consider it, let me tell you how do you get the value. I am just telling you, no need to go through this. Outer sphere का क्या volume होगा? 4/3 pi r cube is the formula. So outer sphere का होगा 4/3 r plus dr का whole cube minus 4/3 pi r cube, right? And when you solve this, you get an expression which is 4 pi r square dr, that multiplied with your probability density. Got the point? We have just took the volume element into account. कौन सा volume? जिस volume में the electron was revolving. So here when I make this plot now for 1s, it looks like this. Okay. Now will that give you the correct picture? ऊपर देखो. Can I attach physical significance to this? It is psi square multiplied with volume element, volume of spherical shell, volume of ठीक है. Now here this volume of spherical shell gives you a diagram which looks like, gives you a plot which goes like this. Okay. And here what does this tell you? That there is a maximum probability of finding the electron, because this was giving you the maximum probability at r is equal to 0. What was this plot called? Probability density plot. And what are these plots called? Radial density distribution curves. Radial density distribution curves. Because अब radial हो गया ना, you are taking the volume element also into account. These will give you the correct picture. That is, there is a maximum probability of finding the electron at some distance from the nucleus. What is the probability at the nucleus? Minimum. And the maximum probability is at some distance away from the nucleus. And for 1s, this A naught is equal to 0.529 angstrom. This is like the Bohr's radius. You remember? 0.529. I hope I am telling you the correct value. 0.529 angstrom. So similarly, if I have to now, this is for 1s. Look up. This is for 1s. Now what will it be for 2s? It will be like, get it? Now there is a maximum probability at a farther distance from the nucleus, क्योंकि 2s तो 1s से भी पीछे हो गया ना. So now there is a maximum probability of finding it at some distance more from the nucleus. और थोड़ी बहुत 1s में तो रह जाएगी, because an electron is like a free particle which is like having a probability of moving here or there. A microscopic particle can never be at rest. Clear with this? Yes. The maximum probability is at this value of r. ठीक है. This value of r would mean that the maximum probability is at some distance from the nucleus. क्योंकि ये 0 था ना, तो 0 का मतलब it is right here. तो अगर r की वैल्यू उसके थोड़े डिस्टेंस पे है, तो इसका मतलब जो हमारा maximum probability of finding the electron is not at the nucleus but at some distance away from the nucleus for 1s. Then at infinity it will be like increasing and the maximum will be at infinity. It will be like one mountain, another mountain, another one, bigger. अब यहाँ पे याद रखना, ये 2s का bigger क्यों है? क्योंकि 2s तो और distance पे होगा ना, तो सेकंड वाला विल बी अ टॉलर माउंटेन देन द फर्स्ट वाला. ये 1s को रिप्रेजेंट करता है क्योंकि 1s also has a tendency to accommodate the electron. So there will be some probability of electron being found in the 1s, but major will be in 2s. समझ आया? ऐसे ही अगर मैं अब इसकी, because there are two aspects. There's a doubt to explain the wave function. Now if I explain the wave function again, wave function is again the identity of the electron. Any microscopic entity, any microscopic, not just the electron. I talk about a proton, there will be a wave function of the proton. I talk about an electron, there will be a wave function of the electron. If there are two identical twins sitting before you, it will be difficult to demarcate between the two. दोनों indistinguishable हैं, सब कुछ same है, तो कैसे identify करोगे? I call him psi1 and the other one is psi2. Correct? This wave function is actually defining your electron completely, and the entire story that we talked about is revolving around your wave function only. Because if you know the wave function and you have the operator of that, of any property, then you can get back the wave function along with the value. This value belongs to your operator. This equation is known as, it is a postulate. Very good. Okay. So now here what we have is, now we've discussed the probability density also. Now when we add the volume element, now what was the problem with the normal psi? Psi has no significance, so that plot will have no significance. So what do? We plot the square of the wave function with versus r, and that gives you the some meaning, but the meaning that turns out to be is not there in reality. So why is it not giving you the correct result even after solution? Because you need to consider the volume element, and the moment you consider the volume element, you get the correct interpretation from the graph, because it turns out to be something like this, right? And on the y-axis you have 4 pi r square psi square dr, where 4 pi r square into dr is your volume element. ठीक है? Now another thing, I talked about, say 1s का radial density distribution. Radial density distribution curve again needs to be explained. Explain the first graph. First graph है, ये मेरा 1s का wave function का मेरे को एक expression मिला. Alright, I got the 1s wave function expression. Then I have a value of r also. Now this psi s will be some function of r. I take r to be 0, मुझे कोई value मिलेगा. I take r to be 0.011, I'll get another value. I'll get another, put another value of r, I'll get yet another value. ऐसे करते करते ना हम एक plot बना सकते हैं. ये कोई पूछेगा नहीं एग्जाम में, सिर्फ समझना आना चाहिए. You know how to plot. एक value x की होती है, फिर आप y में डालते जाते हो and you get another value of y. So this is the plot that you get. Now what is the meaning of this graph? If I say there is a maximum, no, there is no meaning of this graph, because this is talking about your wave function, and it can be either real or imaginary. So what will I have to do? I will have to take the psi square versus r. Now इस case में भी क्या होगा? If say whatever value this is getting, इसका square करूँगी तो the value will just increase, but the plot will be more or less the same only. Alright, the values will be increased, but the plot will be the same. Now what is the meaning of this graph? That when your r is 0, there is maximum, when your r is approaching 0 rather, when your r is very less, there is maximum probability of finding the electron. तो इसका मतलब तो ये है that if this is your nucleus and you have the electron revolving around it, the maximum probability is at the nucleus, which is wrong. So why is it wrong? What are these curves called? Probability density curves. Now if what do I need to take? I need to take the volume element into account. ठीक है? क्योंकि wave function तो मुझे मिल गया from the solution, but I just need to now correct it and enhance its interpretation further. So when I take the volume element, that is 4 pi r square dr. What is this 4 pi r square dr? This is the volume of the spherical shell. Okay? जब हम इसको लेते हैं, now the curve comes out to be like this. This means that there is a, what is the interpretation? That there is minimum probability of finding the electron when r is 0, and there is maximum probability at some distance from the nucleus. That distance for 1s turns out to be this distance. That means you will read the distance from here. This turns out to be equal to 0.529 angstrom. ठीक है? And this is known as your Bohr's radius, represented by A naught at times. Got it? So this is your radial density distribution curves. Now I am saying this is for 1s. If you now have to plot it for 2s, 2s will be something like this and this. This is your node. What is a node? Where the probability of finding the electron is negligible or 0. Okay? So now this is for 2s. Now another thing, look up. This is like the plot that I am getting. But I need to have a picture of the atom also, and I told you atoms are spherical in nature. Sphere jaise hote hain atoms. So in this case, if I have to plot this 1s, it is like this. I told you how many nodal planes for 1s? 0. But I told you for s generally it is 0. If this is for 1s, please look up here. ये जो dot वाला है ना, this is known as a dot population picture or the just the picture of 1s. Dot population pictures क्योंकि मैंने dots बनाए हैं. ठीक है? Simple. जब मैं इसकी एक boundary बना देती हूँ, this is now known as the boundary surface diagram. Alright? And sometimes they are also shown computationally when you find out like this. These are known as the contour diagrams. तो डॉट वाला इज डॉट पॉपुलेशन पिक्चर, जिसकी बाउंड्री बनी हुई है वो बाउंड्री सरफेस डायग्राम्स, और जिसकी लाइनें बनी हुई हैं वो कौन से हैं? कॉन्टूर प्लॉट्स. दे गिव यू द मैक्सिमम प्रोबेबिलिटी, they give you the maximum accuracy till 90% only. That means they will be accurate to about 90%. They will give you 90% of the picture of finding the electron. This figure is also important. What is the maximum probability up to which you can get the accurate results from the contour plots? It is up to 90%. Asked many times in the exams also. Clear with that? Now look, this was for your 1s. Wasted the time. This was for your 1s. Dots, all these are dots. This is for your 1s. Look up. Up. This is for your 1s. Now for 2s. See, for 2s, that means if this was my 1s, 2s will be far away from 1s. Do you get it? So this one, let me draw the boundary surface diagrams. I'm sorry for my drawing. Anyways, this is not an arts class. So this is like for 2s, got it? This is for 2s. 1s was somewhere here. ठीक है? Right from the nucleus. तो ये मेरा 1s है. So this represents, इधर कम होगी dots. क्यों कम? क्योंकि we are talking about 2s picture. So maximum probability will be at some distance from the nucleus. But there is a nodal plane here, nodal area. Alright? You get that? Remember that the number of nodes in this case for when you talk about the principal quantum number to be equal to 1s, for 2s, for 3s, for all the s, 1s, 2s, 3s, the number of nodal planes will always be equal to n minus 1. Please note it down. For 1s, how many nodal surfaces? 0. For 2s, it will be 1. For 3s, there will be 2 and so on. So the number of nodal planes will always be n minus 1. Remember it, you don't need to write stories on it. Then the number of angular nodes. There is another term which is known as angular nodes. Remember? Yes? Okay. Probability density talks about a very good question. A probability density talks about finding the electron in a particular region of space. The question is then how do you define radial density distribution curves? Radial density distribution curves is nothing but the probability density multiplied with your volume element. Alright. So it gives you the probability of finding the electron in a particular volume region of space. Volume region, spherical shell. हाँ जी. Yes. No. Here generally we are talking about the electron. See, basically what do you have the electron? See, understand the atomic structure. You have the nucleus here in between. Then you have the first subshell. What is your first principal quantum number? 1. It is just 1s. It goes like this. The next one is principal quantum number is 2. Now that 2 is actually an orbital. Okay, that is actually an orbital which contains in itself subshells 2s and now 2p. So that is contained within that spherical shell itself. So generally, but it has its own space, that is, it will be like nodal surfaces, because your atom is existing in all the 3 spatial dimensions. So in that space itself it will have one in the x direction, another in the y direction, and the third one in the z direction. So by and large we are talking about this part to be like, jumping. You remember Bohr's orbit was like 1 orbit, 2nd orbit, 3rd orbit. So it was particular. Here we are now talking about orbitals, that is region more than the orbits, and then it is also talking about that orbital comprising of several subshells. Okay. So now where was I? I was talking about the probability density angular nodes. Remember that the number of angular nodes will be equal to L. The number of angular nodes will be equal to, note down the number of angular nodes, that will be equal to generally just the L, because these are the radial nodes. Radial nodes are n minus 1. What are your radial nodes? N minus 1. Now you have the azimuthal quantum number, so you can have the probability, just a sec, L for London, small l, that's the azimuthal quantum number. And just note down that the total number of nodes are given by, the number of angular nodes defined by L is given by n minus L minus 1. No, wait. The number of nodes that for 1s, 2s, 3s are n minus 1. The number of radial nodes, just write down, I am sorry, just correct it. The number of radial nodes is equal to n minus L minus 1. L, n minus L minus 1. The number of angular nodes is equal to L. So what will be the total number of nodes? It will be the sum of the angular nodes and the radial nodes, that is equal to n minus L. N minus 1. See, radial nodes, I tell you, when you solve for the Schrodinger wave equation psi, it is dependent upon 2 parts. One is the radial part, that depends only on r, and the other is the angular part, that depends on 2 angles theta and phi. So when you solve for these, you get your wave numbers, you get information about L and M. When you solve your r, you get information about N. So whatever nodes are generated from these two are known as the angular nodes, and whatever nodes are generated from generally this N, because this is only the radial part, those are known as the radial nodes. That is why you write down the total number of nodes is n minus 1. Now you know that what are the number of angular nodes. Don't make a mistake like me. What are the number of angular nodes? L. What are the number of radial nodes? N minus L minus 1. And the total number of nodes? N minus 1. N minus 1. Now, no, generally when you talk about simply px, now you know that if I am talking about px, talk about 2 nodal planes or 1 nodal plane. When you talk about when you talk about p, there is only 1 nodal plane. Nobody is correcting me. When we talk about p, we talk only about 1 nodal plane. When we talk about D, we talk about generally sometimes like 2 depending upon what is the position, right? No, when we talk about say px, we've talked about nodes before, so you talk about the nodal planes in general. So those are also a part of the angular only, because when you talk about the angular parts only, then only you get information that your P is dumbbell. Now what this is the boundary surface diagram for your P orbital. Now the boundary surface diagram for your D is also accordingly, it's like a double dumbbell, so it's like this, right? And I stated last time, if you're talking about x, that means Px will give you how many? You will have x, y and z. So it will give you how many nodal planes? Now tell me, you have revised. We talk about yz and zx plane, because your Px is lying only about the x axis, right? So the other two forms your nodal planes, and similarly for your D also we do talk about the only D orbital which has no nodal planes is your dz square. Okay, then after this I think you can just try and draw the radial distribution plot for 3s on your own. Just take it as a question and try to draw the radial distribution curve for 3s, all of you all. And let us just revise your PZ and your done with it for 3s. For 3s, how will it look like? The biggest one being the last one. So you will remember? Okay, one more thing that I just missed, that if you're drawing the probability density curve, what is this? Probability density curve for 1s is this, for 2s it is something like this. Just have a knowledge about it. For 2s it goes something like this. Okay, let's talk about the nodes again, because there is a question. The plotting after 2s plotting, what will it be for 3s and 2p? That is the question. Now, if I have, say for 2s, if I talk about say 2s, I have already stated that this is the probability density curves. What are these? Radial density curves. The question is, we'll talk about the angular nodes as well as why dz square has no angular plots. But before that, talking about this question, that after 2s plotting, now this, what was for 1s? The 1s was simply this, which gives you the correct picture. What was for 2s? It was like this. That is, there is some probability in 1s orbital, and there is more probability in your 2s, which is like the second one. In this case, now then I started talking about the nodes and all. The number of nodes for 2s subshell, so for 2s shell will be equal to n minus 1, because your 2s will be like this, and then it will be having, this is for say 1s. 1s is spherically symmetrical, so no nodes. But for 2s you have one nodal surface there in between. Now after plotting, this means that this is for your 1s. You have some nodal surface here, right? And this will now represent your 2s. Similarly, I gave you a question for 3s now. For 3s, you know there will be some least probability in case of 1s orbital, some more probability in 2s, and the maximum probability in the 3s. And how many now? The number of nodal surfaces, 1 and 2. Now I am giving you another question because all of us all were fumbling for p and d orbitals. Let me just remind you, what was the shape of p orbitals? If I am talking about x, y and z is coming out of the plane of the board. If I talk about px orbital will be along just the x axis. Alright, it will only be about the x axis. So how many nodal planes can we talk about? xy means x has it, so that's not a nodal plane. xz, that also has x, so it will have the nodal plane. Matlab there is no probability or negligible probability of finding the electron. So which plane will not at all have your x? That will be yz. So p orbitals will have only one nodal plane. Do not make this mistake again. Got it? All of you all? So just check it out. Your pz orbital, I've just explained it in case of px. Now you tell me how many nodal planes for pz, how many for dxy, and let me just give you dxz square because this is a doubt.
Ma'am, so for the s orbitals we were having only nodes, not nodal planes. For p and
For s orbitals we were talking about nodal surfaces generally because you have your 1s like this, then बीच में थोड़ा सा gap है where also you have a little bit of electrons visible, so negligible or zero, and then you have your 2s here. So बीच में there is like the empty space which is known as the nodal surface. And here we are talking about nodal plane because we are talking about the shape of the orbital which is like a subshell to a main shell. So now you tell me for how many nodal planes will be there in pz, how many in dxy and how many in dz square. Quickly. In the meantime, I'll just go through what all topics need to be now just seen. And you know these are called as the these are what is known as the angular nodes. You remember I talk about the azimuthal quantum number. What are the three quantum numbers that we get? Why is there a higher probability of finding an electron in 2s than 1s? If I am talking about the 2s, the electron in 2s, so that electron will always try to sit in 2s only, but because it is an electron, it will keep on moving because a microscopic entity can never be at rest. So there is some probability of 2s electron to also be existing slightly in 1s for some time. So that is why we draw a small mountain for our 1s, that there may be some probability of finding it to be in 1s, and there is like a major probability of the 2s electron to be present in 2s only, right? Like if I talk about a student in 12th standard, the 12th standard student will be taking the class in his room. But then there is a slight probability that he may want to revise the concepts, that he may come to the 11th standard classroom again to prepare for IIT. Okay? So there is like that probability. Now I was talking, now let's take up, now the next three questions will be taken up now. We have three quantum numbers that we get from Schrodinger wave equation. What are those three quantum numbers? N, L, M. Today's class is focusing on quantum model and quantum numbers only. So get a clear understanding. N, principal shell, azimuthal. N can take up values as 1, 2, 3 and so on. These are your shells. Then you have subshells which are defined from your azimuthal quantum number, which also talks about your angular momentum quantum number. Those values are from 0 to n minus 1. Okay, from 0 to n minus 1. So you will have the values as 0, 1, 2 depending upon what your value of n is. लेकिन हमारे पास ये values तो हमने देखी है. If L is 0, we are talking about which kind? S. This S stands for sharp. I have faintly remembered. So this is like sharp. Sharp as in you get a sharp definition. So maybe because of that, or maybe the name of the scientist. No, it's like because of the maybe the definition. Okay, when L is equal to 0, it is your S subshell. When L is equal to 1, it is your P. When L is equal to 2, it is D. and when L is equal to F, 3, it is F. Okay, now I am talking about number of nodes here. This talks about the shape of the orbitals also. Angular nodes का question है. Radial तो समझ में आ गया सबको. Radial is n minus 1. तो totality में भी क्या है number of nodes? n minus 1. Are you all here with me? Louder? So now if I am talking about pz orbital, so pz में I stated that how many nodes now will you have? You will have, pz means along z axis. Say this is z, this is your x, let y be coming out of the plane now. बोर्ड पे दिखाने के लिए. So it cannot be xz plane क्योंकि z पे हमारा orbital है. It cannot be yz plane because z पे है. So the only nodal plane or the node is like
XY
1. That is xy plane. So the number of nodal planes in this case is 1. And the number of angular nodes is equal to L. So for P, the number of angular nodes is equal to L. Angular मतलब अब मैं उसकी 3 dimensions में I am talking about the shape. Getting the link? Confused. I am, पहले हमने radial nodes की बात करी, radial nodes नहीं, total in totality nodes की बात करी. हमारे main shells क्या होते हैं? 1s, then you have 2 and then you have 3. The total number of nodes is equal to, देखो, n minus 1. That means if I am talking about 2s तो उसके अंदर एक nodal plane surface होगा, 3s तो 2 होंगे, ऐसे ऐसे. Then I introduce the concept of angular nodes. What is the number of angular nodes? L. Simply L. और वो मैंने समझाया कैसे था last class में भी. We talk about the pz orbital. Pz orbital is like about the z axis. So my z will always have my p orbital. ठीक है? तो इस केस में मेरा xy plane जो है, xy is like this plane. That is acting as a nodal plane. So the number of nodes in this case will be just 1. Got it? The number of nodes will be just 1. And I stated this is like the angular node. And this angular node is equal to L. What is the value of L here for P?
1.
So it is 1. You get some link to it? Angular nodes is like when you are talking about the number of nodes in the 3-dimensional space according to the shape of the orbital. Complicated definition, don't need to remember. So समझ लो, ठीक है? फिर उसके बाद जब मैं dxy, let me just finish this up. When I talk about dxy, so if I have my x and y here, so my dxy will be somewhere along x and somewhere along y. Now you will think what is it? Only z axis is the one. लेकिन मेरा एक प्लेन इस साइड से और एक प्लेन इस साइड से मीट करेगा. First of all, I will have two planes simultaneously bisecting each other in the xy position, right? Those two will act as the nodal planes. So ये मेरा angular nodes की बात कर रही हूँ. And what is the number of angular nodes in this? 2. So in this case, the number of nodal planes will be equal to 2. That is equal to L. L means the value of D, with an exception of dz square. Why? Because what is the shape of the dz square? You have it about the z axis and you have a small spherical shell. और जहाँ पे spherical shell आ गया means it is existing in all the 3 spatial dimensions. So in that case, जब मेरा spherical shell, because z is like this and then you have a spherical shell about it. Can you see it in the air that I am drawing? So then there is a spherical shell. And the moment you get a spherical shell, then that means that it is present in all the 3. So there are no nodes. Now, okay, we don't draw for 2p, 3p in radial density distribution curves. You draw. याद रखने के लिए बताती हूँ. This was for 1s. This is for 2s. Okay, this is only from your examination point of view. वरना इससे ज़्यादा I don't think. 1s, 2s and 3s means 3s का तो आप सबने खुद ही बनाया था सही वाला. सबने यही बनाया था ना?
Yes, ma'am.
Alright, so then you have 3s. All these are like 4 pi r square dr psi square. Please remember that your graphs are meaningless without the x and y axis label. Because how do I know whether this r is standing for radius or it is standing for some red color, red intensity, what? I don't know. So it needs to be specified. You need to specify what is this, and normally units are also given along with. Say if this is an angstrom, and here also the units are always there. Dxy means that now if it's easy to understand the dx square minus y square. Shall I explain that? Dx square minus y square is like this is your x, this is your y, okay, and your z is coming out of the plane of the board. So dx square minus y square lie in between these two, okay. अब dx square minus y square में what are the two nodal planes दिख रहे हैं? xz और yz. z तो बाहर निकल के आ रहा है ना, तो ये xz is one plane and your yz is another plane. So how many nodal planes? Two. x square minus y square clear. लेकिन dxy क्या होता है? dxy होता है about the axis. dxy होता है about the axis means ये dxy का representation. dxy डबल डम्बल, ठीक है. अब इस केस में सिमिलरली x स्क्वायर माइनस y स्क्वायर में कौन से दो प्लेन्स थे जो इंटरसेक्ट कर रहे थे? xy and it was xz and yz. Those were the two planes which were intersecting at the nodal point, right? Here in this case you will have two nodal planes, absolutely these two nodal planes which are bisecting at your xy intersection point. Got it? So दो nodes, दो nodal planes. And then thereafter we don't draw for the query. Yes, the doubt was we don't draw for 2p 3p in radial density distribution curves. We draw. I taught you for 1s 2s 3s, ठीक है. अब याद रखना, this is only to remember that when I am talking about these, then 1s was the beginning of this. What is the beginning for p? 2p, ठीक है. So 2p will be similar. I am just telling you to remember. 2p will be similar to 1s. जहाँ पे starting point है, that will be similar to the first of the other one. Then we have, for this we need to do a lot. This will be now for, you tell me, this will be for 3p. Got it? अब अगर मैं पूछूं what will be the radial density distribution curve, did you all get it?
Yes, ma'am.
So now draw the radial density distribution curve for 3D. 3D is the beginning. So जिसका भी beginning जहाँ से शुरू है उसका first वाला यही होगा, ठीक है. I have not given any explanation. I have just made you memorize it. 1s 2s 3s easy था, वो समझ आ गया. तो 2p जहाँ से शुरू होता है the first one will be similar to this. So 2p 3p 4p. D will now follow along with the newer one. Now the first of D is 3D. So you will have 3D similar to this with different values, but the nature of the graph will be the same. 3D will have a maximum probability and this R will be away from 1s 2s. मान लो 1s का यहाँ था हम, 2s का यहाँ था, ठीक है. उन सबको पार करके it will be just like the Aufbau's principle, right? Clear with that? Okay. Then any other question? Difference between radial nodes and angular nodes. Radial is like when you talk about R, ठीक है. R is moving in a particular direction, and angular is when you are talking about other angles like theta and phi. जैसे for example, if I talk about say the radial nodes, these are say three directions, okay, x, y and z. Say the distance of my electron from the nucleus defines your R. So this is some kind of distance. So it talks about the radial part of it. The angle that, say this is my z axis and let y be coming out. The angle that this radial part makes with the z axis is known as theta. ये मैं बता रही हूँ, ठीक है. And the angle that my projection makes with the x axis is generally phi. सो ये थीटा एंड फाई जो है ये एंगुलर पार्ट को डिफाइन करते हैं, और जो ये आर पार्ट है दैट डिफाइंस योर रेडियल पार्ट. गॉट इट? आर डिफाइंस योर रेडियल पार्ट, थीटा एंड फाई डिफाइंस योर एंगुलर पार्ट. सो इसकी नॉलेज से आई गेट टू नो अबाउट द शेप एंड द magnetic quantum number that talks about the magnetic character also. You have it talks about L and M, and your R in general talks about the main quantum number, the principal quantum number, that is N. So basically your the radial nodes and angular nodes have the names from their originating point. Okay, so अब इतना इन डेप्थ में कर रहे हो और फिर भी IIT अगर नहीं क्लियर हुआ तो then it will be very bad. So make sure that if you are understanding to that extent, I just hope you got it. Theta and phi are the angular part. What is the radial part? It is R. What are the number of radial nodes? N minus L minus 1. What are the number of angular nodes? L. What are the total number of nodes? N minus 1. Okay, then thereafter I think we talked about the energy already. The shapes have been discussed. Another important concept now, that is known as the shielding effect. ठीक है? Shielding effect is like easy to understand. Nucleus is there, ठीक है? 1s में electrons है. Then you know what is the Aufbau's principle, that they will be filled in the order of 1s, 2s, 2p, 3s, 3d. This is just to check whether you are awake or not. So this is 3s, 3p, then you have 4s, 3d. Okay, we do the filling in this order. So now I was talking about which point? The shielding effect. Now when an electron will be accepted, okay, when an electron say will be, nucleus is somewhere below this point, okay, hypothetical again, ठीक है, ये कोई एटम तो है नहीं, पर न्यूक्लियस यहाँ पे है. अब यहाँ पे इलेक्ट्रॉन ऐड होगा, फिर 2s में ऐड होगा. ऑल दीज आर लाइक शेल्स अराउंड द न्यूक्लियस. नाउ से supposedly I talk about an addition of an electron in 3s orbital, ठीक है, addition of an electron. तो 3s कब fill होगा? When you have all the inner shell electrons filled. The inner shell electrons are already filled. Now the ones who are already a part of the family try to resist the new member. This is their like trying to shield the nucleus. Who is the head? Not in reality, just I mean telling you otherwise. This is like the main nucleus. Nucleus has the positive charge. Electrons are negatively charged. The interaction between the two is attractive in nature. Okay, from here we will actually carry forward our studies further tomorrow in the next chapter. What you have is, here you have the nucleus, positive charge, electrons filling in the subsequent shells, negative charge. There will be attractive force. So the moment an electron gets added up in the outer shell, there should be some kind of an attraction. So the size should decrease because attract करेगा, खींचेगा अपनी तरफ. But net effect कई बार क्या होता है कि ये जो अंदर वाले electrons हैं, they will also pose a repulsive effect because like charges repel each other. So there will be some kind of a shielding provided by these inner shell orbitals. Got it? There will be some kind of shielding. So the moment the first electron gets added, there will be a अच्छा खासा attractive force between the two. But when the last electron, all the electrons are indistinguishable in nature. So there should be no bias or discrepancy in the way the nucleus is trying to attract the electron. So in that case, there should be no bias for this also. But because when it comes, there are already inner shell electrons which are already filled in, they will try to shield the nucleus. They will provide a shield to the nucleus so that the new member does not interact as good as they're doing. So because of that, there is not much of an but still the electron added to the same shell will always reduce the size to the same shell. I repeat, the electron added to the same shell will always reduce in size because the nucleus will try to attract. So that thing remains. ठीक है, लेकिन जब हम शेल ही एक इंक्रीज कर देते हैं, पूरा 2 से 3 में जाते हैं, तो देयर इज फुल शेल व्हिच इज गेटिंग एडेड अप, सो द साइज विल increase when a shell is added, but if the electron is getting added up to the same shell, size will decrease. Correct? Right? Now supposedly if you have 5 more members coming here, you will always occupy this seat, the seats that you normally are in the habit of occupying. You will try to repel and ignore the new members. Why? Because you want to interact more with the teachers who are standing here than the other students. Just giving you an analogous example to remember. Shield means that these electrons are trying to shield the nucleus, and this will now be I mean, if say if you have P2 and you are adding another electron, say the third electron, or if you have say let this be the case, so then this third electron when added up will result in decrease in size, but not to that great an extent. The attractive force will be lesser than the normal electron proton interaction because of the shielding effect. But shielding का effect का मतलब समझ में आया, that the inner shell electrons will try to repel the incoming electron. Clear with that? This is one thing. Let's take up some questions before we move on with any other topic here, because now we'll just encroach into the otherwise the periodic properties, because from here it goes in continuation. Just check up some, let's check up the first question. First question here. Check the first question. What is the principal quantum number of the first shell to have d orbitals?
3.
First shell to have, I want the answer from everyone in chorus.
3 options.
Not one student, but all of you all should be clearing the paper. So the answer should come at the same time from all of you all. Okay? What is the principal quantum number of the first shell to have d orbitals?
3.
3. Because it starts from 3d. Why? Because n is equal to 3, then L is equal to 0, 1 and 2. So it is possible only when n is equal to 3. Next question. S orbitals have an azimuthal quantum number L of 0. Very simple. So louder and clearly from all of you. Next. Question number 3. P orbitals have an azimuthal quantum number of 1. That's also clear. Then the next goes in coordination, so that you, so that's 2. Okay, because that's talking about D now. Now next question. There are how many values of ml for L is equal to 2? This is equal to. For L is equal to 2. For L is equal to 2, what are, why are only some are answering? Open up the bulb here. All of you all should be answering. Even there, I mean, even if you just sitting within a room, you should be answering this question. L is equal to 2 means what are the values of M? -2, -1, 0, +1, +2. These questions should be solved within seconds, not even fraction of a second. So that will be 5, the answer to that question. Which quantum number describes shells and size of the orbitals? Principal quantum number. Those of you who are like sleeping, please get up. Next. Which quantum number describes the shape? Azimuthal quantum number. Very good. The places where electronic probability distribution functions are 0 are nodes. Okay. Which quantum number describes the orientation? Okay. Yes. Orientation is described by the magnetic. Shapes by? Shape. देखा आता है तो सब कुछ ऐसे जल्दी जल्दी में फिर करोगे गड़बड़ कर दोगे. Then which quantum number determines the energy of an electron in a hydrogen atom? Energy. Energy. N. Why a doubt? I am disappointed. Which quantum number will describe the energy? N. Because principal quantum number is the one that gives you information about the energy. You remember? Okay. Then next question. The spin quantum number is a result of? Now, I told you spin is something that you do not get from the Schrodinger wave equation. ठीक है? I told you that it was determined and accidentally also by Stern and Gerlach. उनका नाम तो नहीं है. But which rule can you relate? What is Aufbau's rule? Let's revise. The one in which the electrons get filled according to the order of energy. No relation. Pauli's exclusion principle. No two electrons can have all the same quantum, all the quantum numbers the same. But N, L and M.
Can be the same, so S has to be different.
N, L and M are same, can be same for say 3p, for 3d, all of these have N, L, no, for 3px, your N, L and M will have the same values, but the last value which will be different will be for S. So this is somewhat related. Another relation is that only two electrons, this is also your Pauli's exclusion principle,
Can reside.
only a maximum of two electrons can be accommodated. So if two electrons are like this, they cannot be accommodated. So Pauli's exclusion principle. Do you want me to discuss the others also? Sure.
Yes, ma'am.
Quantum numbers are arithmetical values, numerical values, geometric values, logical values. Numerical values, because these have been derived quantitatively. There is a proper derivation, solution which is actually there. And remember that Schrodinger's quantum mechanics is based on his wave equation, which is dependent on the wave motion. Heisenberg gave it in terms of matrices, so his is known as the matrix mechanics. Okay, that's clear to everyone. Then we next move on to, so remember that these are numerical values. And next, use of quantum numbers is to specify the electron's position. There can be a confusion between energy and position, but if you know the position, you will be exact. Calculate the energy, you will be able to actually talk about the shape. If I am saying that the electron is sitting on 3px, so you can find out the energy because you know 3, you can find out the shape because you know p, you can find out the velocity according to Heisenberg's uncertainty principle. Because how will you find out the velocity? It is delta x into delta p is greater than or equal to h upon 4 pi, right? And your p is m delta v. Your p mass is constant, mass to delta se bahar hi aayega, so it will be m delta v. And remember that mass will change only when your particle is moving with the speed of light. Have you done this?
Yes, ma'am. Yes, ma'am.
What is this called? When you have, this is was given by Einstein, that m is equal to, this is the theory of relativity. Theory of relativity, that m becomes equal to your m naught upon under root of 1 minus v square by c square. That when your particle is moving with the speed of light, then your mass only has the probability of changing. So this is, and let me tell you, Schrodinger wave equation also has a problem. This is not the final thing. You will be studying it. Theory of relativity was not taken into account. So when theory of relativity was taken into account, we have done atomic models till quantum. When the theory of relativity समझ में आ गई? That the mass will change only when the particle is moving at the speed of light. अभी तो छोटे-छोटे particles and they may have the tendency to move with the speed of light. So when you talk about the theory of relativity along with Schrodinger's model, then a model was given by Dirac, D-I-R-A-C. That model was given by Dirac. So theory of relativity was considered in it. Okay, and then let's talk about the next question. Azimuthal quantum number actually represents your subshells. Answer it quickly. Azimuthal quantum number actually represents your subshells. Quantum numbers are used to describe. Let's just do one or two questions before we talk about. What was the question?
Quantum numbers are used to specify.
Quantum numbers are used to describe proton, nucleus, electron, positron. Quantum numbers are generally in atomic structure. What are we using the quantum numbers for? To specify your electron. So the answer is electron. I stated that each of these microscopic entities has an individual wave function. But अभी हम quantum numbers की बात कर रहे हैं, and we have solved our quantum numbers to describe the electron. Okay. Letter S for azimuthal quantum number stands for, oh luckily I told you S For P, D and F, I'll just find and be sure and then communicate. Okay. P is not for, because principal quantum number is your N. So do not get confused. Right. And now here, from here, we actually encroach into, it talks about bond order. So this is like a new concept that I think we'll just take it up tomorrow. That when we talk about the periodic properties, let me just explain. हमने atomic structure पढ़ा, that means we gain knowledge about just an atom. We gain knowledge about atom. तो उस atom का एक orbital होगा. That will be called as an atomic orbital. Okay? That atom, when combines with another atom, forms a molecule. Simple बोल रही हूँ. We have one atom, we have another atom. When I make the two atoms interact, they will form molecule. जैसे hydrogen atom and hydrogen atom will form H2 molecule. Oxygen atom and oxygen atom will form O2 molecule. So remember that a molecule is formed, or a molecular orbital. अब जैसे हमने orbital की बात करी, remember that whenever you talk about orbital, you are talking about some probability of finding the electron in some region of space, and that is not in particular a well defined region. There is a probability in some region. Okay, so when we talk about an atom and an atom, the combination of two atoms forms molecule. I am now extending your knowledge to the level that I am saying now. We've talked about atoms, we've talked about their subshells. So if I talk about, just reminding you of one of the most important, did you do copper? I told you how to write down the electronic configuration for this. Copper is number Skartai Vakraman Fico Niku. That is 29. So that is 29. Now for a particular atom, I can write down these. Each of them are like orbitals. What are, I define 1s2, 2s2, 2p6, 4s2 and 3d9 initially, then I write it as 3d10, 4s1 for this. So these are actually the orbitals associated with the particular atom. But now when an atom is completely formed, because all these electrons combine to form your atom, these atoms will have an atomic orbital. Okay. Now when one atomic orbital combines with another atomic orbital, it forms your molecule. Clear? Now why am I saying orbital? Because जो interaction होता है, that is majorly from the outermost shell, which is very importantly called your valence shell. Okay, so now if I talk about this, then atomic structure, the application of atomic structure that you have done now in this particular topic that we've just covered up will now be taken further to understand molecules. Now each of your, like if I'm talking about hydrogen, what is your hydrogen? Simple, 1s1. So 1s1 is represented by this. This is an s orbital. I've just written a plus sign just as a convention. Okay, it's like the same charge throughout. Okay, otherwise 1s1 is like an electron. If this hydrogen combines with another hydrogen, what is that? That is also 1s1. So both of them will combine. Okay, this hydrogen atom is combining, this is like 1s, this is also 1s, 1 electron, 1 electron. When they will combine, they will form your H2 molecule. बात समझ में आ रही है? Now I am saying that a molecular orbital will be formed by the combination of two atomic orbitals, and this is what we will actually study in the next, after studying the periodic properties. What have we done till now? We've understood an atom. It was not that easy to form the atomic structure, right from Lewis-Sippers, Democritus, Dalton, then you had Planck, J.J. Thomson, Rutherford. How can you forget important contributions? Rutherford, Bohr, and then you had Schrodinger. Schrodinger along with Heisenberg. His work also needs to be remembered. Okay, so all these people developed your atomic structure model. Now after and understanding the atomic structure, please practice as many questions as you can from this. Then we'll carry forward the story with your periodic. Now we've looked at the atom in totality. You know how to write down the configuration. Now look at its properties. We look at the atom's properties. Okay? Tomorrow we'll start with periodic properties, and in that we'll actually go through the properties of the atom, how they change when we actually add an electron, take an electron, or I mean what kind of tendency do they have, what is their behavior towards other electrons. Like, if I be friends with you, I will now be interested in what are your properties, how is your nature, whether it is giving or taking, whether what kind of tendencies you have. So all this and more we'll do it in the next topic, right? We'll study the periodic properties, and another thing that I've actually set the base for is that the combination of two atomic orbitals will yield your molecular orbitals. Okay, why does d orbital offer comparatively lower shielding effect? D orbital offers relatively lower shielding effect because of the positioning of the d orbital. See, normally you have S. S is like very strongly associated. What is the shape of S? Spherically symmetrical. P is like a little complicated, that is that's single dumbbell. You have just a dumbbell. D is even more complicated, that is double dumbbell. So rather than interacting with the nucleus, it needs to concentrate on its shape as well. Take it like that. So what happens in case of d orbital is like, because they're like more scattered in nature, their shielding effect in comparison to S and P is lesser. And F, S, P, D, and then you have another orbital which is F. F will have even lower shielding effect. So the strongest shielding effect will be that of S, followed by P, followed by D, followed by F. Thank you for the question. Okay, and then thereafter, once we go on to the molecular orbitals, then we'll take up these questions of bond order and all. So basically you remember that atomic structures, when there are two atomic orbitals, now you understand the concept of atomic orbitals. The combination of two atomic orbitals will give you a molecular orbital. And just go through, and another thing is, another question that somebody else asked, I felt in between, was like, in Hund's rule what you have is, generally, what is your Hund's rule of maximum multiplicity? That you generally have each orbital getting singly filled first.
And then pairing will be done.
Now for this there are two reasons which are actually given. One reason is that there is like best symmetry, because this question was asked in one of the subjective papers as well. One of the reasons for Hund's rule, why is it like a principle, is that each of the electrons is like symmetrically distributed. I give 1, 1, 1, 1 to each, that's like symmetry. And always, whenever you have in chemical nature or in natural places, you will always look that nature looks for symmetry. So because one reason is symmetry. The other reason is that you have an electron. This electron can actually interact with this electron because they are of the same nature. Both of them are like with the same spin. Okay? One reason I stated is for the Hund's rule is symmetry. The second reason is that they can actually interact, and when they will interact, this electron may come here, this electron may come here, this electron can come here, this can come here, or they can exchange in the maximum possible way. So when there is such kind of an exchange, that leads to something which is known as exchange energy. So the exchange energy will be maximum in this case. And something else that I have given you an information about previously, that was the spin multiplicity. You remember that the spin multiplicity is maximum. How do you define your spin multiplicity? That is S into S plus 1. That the total spin in this case will be half. If this is plus half, this will also be plus half, this will also be plus half. So the maximum spin is in this case, which is equal to 3 by 2. If I talk about any other case, if I talk about this or this and this, so then this will be plus half, minus half, plus half. So the total spin will be plus half. Do you get that? So in that case, the most stable according to Hund's rule will be this, because this also is giving you the maximum spin and hence the maximum spin multiplicity. So in this case, also remember that the reasons which support your Hund's rule of maximum multiplicity is, one reason is that you have symmetry, the second is that it talks about the exchange energy, and the third is that it is also giving you the maximum spin. Okay? Stability for that particular system. Yes, go ahead with your doubt.
Can an electron change its spin quantum number?
the electron can have a particular spin quantum number, but basically your atom is already existing in nature like that. ठीक है? Then in that case, yes. The question is, can an atom change its spin quantum number? Okay, now say if supposedly I have neon. Neon is 1s2, 2s2, 2p6. So it is already completely filled. So in that case, there is just no possibility. Let's talk about sodium. What is sodium? 11. You should be telling that before me. Sodium is 11. So 1s2, 2s2, 2p6. 1s2, 2s2, 2p6 and 3s1. Now the question is whether it can change its spin multiplicity. मान लो पहले प्लस हाफ है वो माइनस हाफ हो सकती है. Clockwise and anti-clockwise are kind of degenerate. अकेला इलेक्ट्रॉन है, उसके पास स्कोप है कि वो ऐसे भी जाए, but the maximum preferred position would be the most comfortable one. Okay, so it will go in the plus half, but otherwise minus half and plus half both are possible. Now the question goes beyond that. The question is, can this change spin quantum number when it is interacting with others? Yes, of course. I mean, see, when an electron is interacting, there will be various movements of the electron also. And in that cases, it is like a chance that rather than spinning now clockwise, it moves anti-clockwise. And then your physics also comes into play. You study about diamagnetic, paramagnetic, that's all a play of the motion of the electrons or the domains which actually arrange themselves. So basically your spin quantum number can either remain as plus half or minus half when the electron is like free. But it would like to be in the most stable state in accordance with the rules. We've done our Pauli's exclusion principle, Hund's rule of maximum multiplicity. And Aufbau's is for filling of the electrons, generally. Hund's is talking about basically filling of the electrons singly first and then pairing. And your Pauli's talks about the two spins, that is plus half and minus half, both exist for the electrons. So good question. The size of the molecular orbitals will be more than the atomic orbitals, yes. Because atomic orbital, see, you stand and together with your sister or your twin sister or your soul sister, your size will obviously be greater than either of the two of you. So whenever an atomic orbital combines with another atomic orbital, the size of the resultant molecular orbital will always be greater than the initial one. And how the size actually fluctuates with these atoms, we'll see tomorrow. Alright?
As you told that S is determined experimentally. So like
S is, remember when I say S is determined experimentally or accidentally by the Stern and Gerlach experiment, I am talking about the spin quantum number and not the S orbital.
Ma'am, how come it is determined? Because we don't know, it can exist either as plus half or minus half, and it can change as well. So how can we determine?
See, experimentally it was like, I tell you, Stern and Gerlach, when this experiment is given very nicely in a book called Atkins. Too high for your level, but what they actually studied was like they found it that the electron is capable of moving clockwise and anti-clockwise. And from there they stated that it's not just one spin, there are two spins which are possible. It was only when this nature was observed, and then it helped us a lot to understand chemistry further. So we all must thank all the scientists who've created all this. Alright, and I must thank you for your patient listening, but I will thank you finally only after you clear the paper. Thank you.